As you don't know, he is a professor at the University of Minnesota. He finished, two things I want to remember. First, he went from high school to grad school, to the whole undergraduate, which I think he skipped the fun, but that's okay. And he published his first paper when he was 17 years old. He's very proud of that. I think this year is his 50th anniversary of your first paper, right, George? 40th. Oh my God, I make you older. That's the first mistake. 40th anniversary of the paper, but he was 17, he published first paper. But also, when he was at Rockefeller University, he and Bruce Merrifield wrote the first big chapter in Meinhofer's book about solid-phase peptide synthesis, and that was a must-read for everybody who started doing solid-phase peptide synthesis. They put everything together. He put a lot of his time on work on that, and really this is the first work, comprehensive work on solid-phase peptide synthesis. Without any further ado, please, George, give us the history and the recent advantage in solid-phase.
Well, thanks a lot, Wally, for inviting me. I'm still alive. All right, so a few years ago, my wife and I were watching one of these award shows on TV, and they gave an award to someone named Milton Berle. I don't know if you've heard of him, but he's considered Mr. Television from the 50s, right? And so he got up, this doddering old man, and he said, I've received many, many awards in my life, and of all the awards I've ever gotten, and thinking, God, get this over with. He says, of all the awards I've ever gotten, this one has to be I've gotten, Emmy, and this one has to be the most recent. And it was just fabulous, the timing of this guy. And so when I use a title like recent, okay, so I'm going to try to tell something that happened in the last few years, but I've also been asked by Wally to reflect a little bit on the history, because there's a whole generation of great people who are no longer with us, and I want to tell you a little bit about them, because maybe I remember them from my childhood, as I'll tell you. Okay, so. And so we are instructed by the University of Minnesota, to say that we are driven to discover. I don't know what. And we've got websites, and my hobby is writing puzzles, as you well know, and I'll have a couple of comments about that as well. So this is one of my favorite quotes. It's something I still read when I was at Rockefeller, a book edited by Weber. And you all have heard that Isaac Newton is supposedly said to Robert Hooke, this is Newton, this is Hooke. Whoops. Got to learn how these modern newfangled electronic devices work. Okay, so if I've seen a little further, it is by standing on the shoulders of giants. But of course now, with 90% of all the scientists ever lived still alive, this has to be updated. So we are now uniquely privileged to sit side by side with the giants on whose shoulders we stand. So in 1999, so that would have been 13 years ago, I had the privilege with Greg Fields of co-chairing the American Peptide Symposium in Minneapolis. This is our logo with a spoon and cherry. And here are some giants. There's Bob Hodges, who, as you know, is up less than a half-hour drive from here, unless you're taking the shuttle, in which case it's more like 2 hours. This is Bruce Merrifield, Raoul McEnany, a great benefactor to the field, and there's Ralph Hirschman, all sitting in the first row, anxious for things to get moving. And one of the things I'm very proud of that we had at the meeting was a session called, again, remember, this was 1999, Perspectives for a New Millennium. And I don't know if you recognize this guy here, the man from Tucson. Again. And he ran a peptide symposium in 1983, which is of great significance to me because I thought I was in love then, and went back to Minneapolis and started dating my future wife. right after that meeting. There's Charlie Dieber, who ran the Toronto meeting, and is just a real genius polymath. He's the one who got me into crossword puzzle construction. There's Tom Muir, one of the newer generation. There's Bob again, Bruce Merrifield, Robin Offord, who's done a lot of great science and important in the Peptide Society, is the late Murray Goodman. Arno Spatola was one of Victor Ruby's first graduate students, and he tragically died prematurely. That's Stan Weber, and this skinny guy without a beard is me. And so, as mentioned, how did I get interested in puzzle? Other than the fact that Dieber's told me it was a fun thing to do. As you're getting older, you need something to keep the mind sharp. And so you notice that the title of the puzzle is Very Justified Honor, and that is abbreviated as VJH, as in Victor J. Ruby. And I have to say that Victor's been a great friend and mentor. He's never at a loss for words, and when I ever feel particularly discouraged, I can always count on Victor to have a short 2.5 hour long conversation to cheer me up. And so I thought the least I could do was write a crossword puzzle in his honor, and I hope you all tried. I understand they've linked this now to the main page of this symposium. I think there'll be some nice surprises. You may learn something about Victor that you didn't know, maybe that Victor didn't know, especially the answer to this long one, okay? Now here are a few more drawings. Now most of the people in this picture are Bruce Merrifield and somebody else. So this is Bruce and John Stewart. And Victor, do you know where this picture was taken? When? That's right. In some Mexican place that wasn't air conditioned. And this is Bruce with his first graduate student, Garland Marshall, another brilliant man and pioneer. Whoops. And this is Bruce with his life partner, Libby, who still survives him. The story is that Bruce graduated from UCLA one day in the June of 1949. Next day got married. Next day took that cross-country trip to New York City to start his career at the Rockefeller. And this, what's he doing in this picture? This is Miklos Bodansky. And there's another kind of connection to the Divino loop. Now, Miklos was Hungarian, and he actually knew me before I was born, because my mother ran the only analytical ultracentrifuge in all of Eastern Europe, and Miklos had made some peptides, maybe even small proteins, and needed to have them characterized. He then, as so many of us, left Hungary during the revolution. He spent some time at Squibb. Then he had a long career and collaborating with his wife, Agnes, at Case Western in Cleveland. And in fact, when I was looking for an academic job, I had a choice. I had two offers on the table. One was to essentially take over Miklos's lab at Case, and the other one was to start from scratch at Minnesota. This slide was emailed to me yesterday by his daughter Ava, who lives in Princeton, maybe half a mile from my son Michael. All right, so small world, isn't it? And now this is a headline from the New York Times on January 17th, 1969. The main above the fold headline was that they finally decided the shape of the table to have the peace talks to end the Vietnam War. This is maybe a couple of days before Nixon took office. And they had just held a press conference at Rockefeller announcing the first synthesis of an enzyme. And with hindsight, this may have been a few years premature. If they maybe held off a little bit and done experiment properly, maybe Merrifield could have had his Nobel Prize a lot sooner than 1984. But there's Ralph Hirschman from Merck. This Denkewalter also from Merck, and he was just the bureaucrat who made sure the peptide research could be done at an industrial complex. That's quite amazing in retrospect. There's a model of ribonuclease. in the background is a machine that was used that is now in the Smithsonian. This is Bernd Gute, the German postdoc who did the work. Actually, he had been given a very simple project. The project was this. So you know that ribonuclease A can be cleaved by subtle lysine to form the S protein and the S peptide. And in fact, the S peptide was studied for a really long time by people like Klaus Hoffmann. And so, in fact, the Merck team made ribonuclease S because ribonuclease S could be reconstituted with the S peptide, and they kind of complemented each other and got full enzymatic activity. So ribonuclease has active site histidines both very early in the sequence, histidine 12, and very late in the sequence, histidine 119. So you need both. And so that was the S peptide S protein system. Well, so Gute's project was to have something similar on the C-terminus side. So they chopped off a few amino acids with carboxypeptidases, and there was some other enzyme they used. So 119 was gone, and then they put back a 14-mer that kind of took a little bit of protein, got it sort of out of the way, and went back and then constituted. And so that was the project. But one day, Gute must have felt bored, and he made his 14-mer, and he decided to keep going, and he went all the way, because it was C to N, all the way to number 1, and he got it, and then the problem was there's a humongous purification job, and there's all sorts of tricks, but it was a very, very important contribution, and really inspired me. And this was just basically one postdoc working in the lab with a technician, and it was a genius of Bruce Merrifield supervising. Whereas the Merck team was huge, and it's Ruth Nutt somewhere in that picture. She must be the one with the lab coat. And there's some more of the closer to the Merck team. That's Dan Weber, Fred Holley, and there's again Hirschman and Denke-Walter. So now a year later, I went with my parents to Interlaken, when my father was a speaker at a biochemistry congress, and I wasn't so interested in looking at the Alps and stuff. I wanted to go to some science. My father specifically told me, because I wanted to hear this talk about peptide synthesis. He said, "Oh, George, that's too complicated. You have to think about protection of methionine and cysteine," and those are fighting words. So I've been interested in these sort of things ever since. And so, in fact, my very first paper, some 40 years ago, was on the synthesis of an octapeptide that binds ATP, and the affinity is something like millimolar, and not too shabby. And it came from the active site of the muscle protein myosin, which has been the focus of my parents' research career. And interestingly enough, it was written up in the very next edition, the second edition of Leninger's textbook. I learned biochemistry the summer before in the first edition, and by the next edition it was already in there. That's quite an unrealistic way to start one's career, but anyhow. Oops, excuse me. Again, this was presented at Cold Spring Harbor Symposium. This is the only place my name and my father's name both appear on the same contribution to literature with Merrifield at a Federation proceeding. My father felt it was better to leave his name off the full paper. But this is at the Cold Spring Harbor Symposium, me in tennis shorts, my dad and my mom. And I should just mention on a sad note that about a little over a year ago, my parents both passed away after almost 62 years of marriage, and it was actually 6 weeks apart. So kind of bittersweet, but poignant, nevertheless. And my parents were also married the same year as the Merrifield. So, if you submit a proposal to NIH, they want it to be hypothesis-driven, and that's not the way I approach science. I'm Curious George, right? And I happen to be curious about the following fact, that the ribonuclease synthesis, as impressive as it was, relied on what we now refer to as Bach chemistry. And in Bach chemistry, you have the same mechanism to remove both classes of protecting groups. And by that, I also throw in, for good luck, the signature feature of solid phase synthesis, which is to do it on a resin. That was a truly revolutionary idea. But still having two classes, both removed by the same mechanism, in this case acid, forces you to make the final acid a very strong acid indeed. So you see here's a standard linkage to a Merrifield resin. There are some benzyl-type sidechain protecting groups. And here's the Bach group that was developed by Lou Carpino, another great man in the field. And so the classic groups in orange have to survive repeated exposure to trifluoric acid, which is what you need to take off the Bach group. And that means that by the time you have to take off the rest, cleave from the resin, cleave off the remaining protecting groups, use HF. Now, ribonose is one of the very few substances of interest to biologists that survives HF. HF is a vicious substance. It'll, for example, deglycosylate anything. It'll take the phosphates off. So I instinctively knew that if peptide synthesis techniques were going to make an impact in biology, you had to have milder chemistry. How could you do this? The idea was to have two complementary mechanisms of removal protecting groups. And again, based on having been a lab rat with my dad, I knew a little bit about cysteine chemistry of disulfides. I knew that disulfides are very easily formed and disulfides are very easily cleaved. So I conceived somehow this dithiasuccinoyl or DTS protecting groups that is removed under very mild conditions by reduction. You don't have to cram your eyesight because I'll show this in bigger and later, but this is a completely complementary method. And again, because I at Stuyvesant have been a bit of a math whiz kid, I knew what the word orthogonal meant. It's very widely used in math. For some reason, even though implicit chemists have been using it all the time, it had not been explicitly stated in the chemistry literature. And so kind of by default, I'm responsible for introducing the word orthogonal into the chemistry literature. I understand it was also being batted around by Dan Kemp at MIT around the same time. So if you have a completely neutral way of removing this group, but in spite of that, the DTS group is also very stable to other conditions like very strong acid or light. So that means you could frame shift the scheme to here. You have the T-butyl type groups that formerly used there as a permanent protected groups. You could add some electron withdrawing groups. This particular version is the Wang resin. Other ones came along later. And then have the final step being TFA, which relatively speaking is much milder. It should be possible to make phosphopeptides and glycopeptides and a lot of other interesting things. So that was the idea. And finally, I'm going to close out what I would consider the introductory portion of this talk by thanking Wally again for reminding everyone of this review article that I had the privilege of writing. I took a whole year out of my career, and it's the best thing I ever did because here's how it worked. So Merrifield published this paper in 1963 on solid phase peptide synthesis, and I'll say a little bit more about that as well. It was an entirely experimental paper, and he believed that anybody who published solid phase peptide synthesis who was civilized should quote that paper. So then we forward cited anybody who ever quoted that paper. We sent the secretary to the library to photocopy it and put it in a big file cabinet. So we had about 2,000, and this is all done manually. This was not, we didn't have SciFinder or computers or anything like that. And so then Hans Meinhofer at Roche, who, as you know, ran the first or second, one of the very early American Peptide Symposia. But he had this idea with Erhard Gross, who died tragically on the Autobahn a few years later. But they had this idea of writing this comprehensive series called the Peptides, basically everything you ever want to know about peptides. And so they pitched this to Bruce Merrifield, and he came to me and said, you know what, every time I try to write a review a little bit differently, and it always winds up coming the same. And he charged me with writing a truly different approach. And I took this assignment very seriously and learned an enormous amount in the process. So we remember Hans and Erhard for having had this idea, and I'm glad that by having the Meinhofer Award and giving it to such a great scientist as Victor Ruby, we keep the legacy going. So the dithiasuccinyl group, as you can see, it has a nitrogen. That's the one we're going to protect. And running around the ring is a carbonyl, a sulfur, another sulfur, and carbonyl, and we're back to the 5-membered ring. This had actually been described in the German patent literature as a pesticide. And we realized, and that we worked at the detailed mechanism, but just in principle, anything that will reduce the disulfide, think of it as adding 2 hydrogens. Then it allows carbonyl sulfide to be lost twice. Carbonyl sulfide is, of course, just a sulfur analog of carbon dioxide. That buzzes off. The hydrogens wind up on nitrogen. So then can be considered as an amino-protecting group. And the original vision was to have this as an orthogonal protecting group for the N-alphamine to be used, removed at each and every cycle as a temporary group, so we could implement this orthogonal scheme. For those thinking ahead, that is in fact a vision that was completely successfully implemented beyond anybody's wildest dreams with the FMA group. Also, incidentally, devised by Lou Carpino, but really popularized for the first time by the Roche group of Meinhofer, Art Felix, and I don't know who else were heroes of that effort, as well as the English group of R.C. Shepard and Eric Atherton. But we also found that the DTS could be used in the synthesis of PNA, peptide nucleic acids, and both in our lab and independently in the Danish lab. It could be used to protect the side chain of glycan, so it could be used in glycopeptide synthesis. But there's another mechanism for removing the DTS group, which is both good and bad, and you can think of it as a masked isocyanate. If you pluck out one sulfur, say with a trivalent phosphate, then it becomes pentavalent, and then you lose carbonyl sulfide, you can get isocyanates. And there are a lot of ways you can set this up. You could use it as a very mild way of generating isocyanates. You can also turn it around and use a sulfurizing agent for making phosphorothioate DNA or antisense, nonsense, you name it. So these are all applications of DTS that we and others have pursued. And in terms of how to make DTS, we have a number of methods, and without really dwelling into the details, they're not completely attractive because they are multi-step. First, you have to derivatize the amine, and then after you do that, you have to treat it with this very interesting reagent, chlorocarbonyl sulfonylchloride, that was found quite accidentally when they were trying to purify something called perchloromethylmercaptan, a very, very cheap but toxic compound, and some water got in and hydrolyzed. This is a great reagent, gives you the DTS heterocycle in one swell swoop. And this was, although it's mainly in the patent literature, it was described in a review article in Angewandte Chemie, which I was absolutely positive that the Merck people had read, because the same so-called ETC precursor also gives rise to N-thiocarboxy anhydrides. Now, as you know, the whole method of the Merck group involved controlled polymerization of N-carboxy anhydrides, and there's just a couple of amino acids which didn't work very well. In that case, they thought, let's replace the oxygen with sulfur. So I was absolutely positive that the Merck group must have known about DTS, and this was confirmed years later when I saw Dan Weber at a meeting and said, we had a bottle of that stuff in our lab, but we couldn't figure out how to get it off. We treated with base to remove the ethyl ester, and of course it killed this amino group as well. Well, this is the whole essence of orthogonality. When I had to get rid of the ethyl ester, I used refluxing concentrated HCl, and it came off without touching the DTS group. So, sometimes being young and not knowing everything is an advantage, because I'm sure I could have talked myself out of doing that experiment. Well, so a lot of people in my lab worked on this after I left the Murphy lab. Our original paper was the Jack's paper in 1977, which essentially was the essence of my PhD thesis. And that's also the paper in which the word orthogonal was introduced, but then Ursula Słomczyńska, who then had a very good time in St. Louis with Garland Marshall. Samuel Zalipsky, at that time he was known as Shmuel, but he decided to Americanize his name, as one of the real pioneers in PEG. And then some guy named Bob Hammer, who's in the audience. Laj Guerra, who left my lab and then basically became John Stewart's right-hand man for many, many years and is still there. Lin Chen, who's also in the audience, with Bob Hammer and an undergraduate, Tracy Thompson. So we had quite a lot of knowledge about this chemistry, but there was something that was just, I didn't like this idea that it was two steps. So I had this idea, it's very, very obvious, that this putative reagent, bischlorocarbon disulfame, which actually had been described in the Japanese literature and the German literature, but in very low yields, and we figured out a really great way of making it, as outlined in this slide. This should work in just one swell swoop. Just put in with amine and you're done, right? It should be great. But you know what? It didn't work. You did get this intermediate. We were quite confident that we had this intermediate. But instead of losing HCl like it's supposed to and heterocyclizing, it just fell apart and decomposed. So I was stymied. What do I do now? Well, just like, getting ahead of myself a little bit. Okay, so the idea here was, and this is something that Bob Hammer and I had batted around when he was still a graduate student in my lab. By this time, he was already a full professor with a chair at Louisiana State University. We had this idea that if we replaced the leaving group, which was HCl, with TMS chloride, which was neutral, maybe this chemistry might work. But we couldn't really test this in the lab until my son. I mean, this is the hardest way to recruit collaborators. You have to breed them, basically, right? I mean, this was planned for a really, really long time. I mean, right? But there's Michael J. Barany, who was 17 years old at the time. Bob Hammer. This is Bruce Merrifield's last paper in Jackson 2005. I felt it was only fair, since the problem really dated back to my thesis work in his lab when I couldn't solve the problem. But now we solved it. Just using the TMS group on the nitrogen, it works like a charm and gets the heterocycle, and 2 TMS chlorides are formed. And as mentioned, this is Bruce Merrifield's last published paper. And when we submitted it, the referees loved it, the editor loved it, but you know who didn't love it? The production manager. They said you cannot have initials in the authorship because it'll mess up the search functions or something. So I discussed this with Bruce, and he said, I will never forget this, tell them that the 5th most cited paper in their history of their journal was written by R.B. Merrifield, and it was good enough then, should be good enough for this paper. Well, still working on this problem, and this slide. I can't expect you to digest everything, but I think we finally got this nailed. We came up with a variation where the reactions are slowed down enough that we can observe them. We can isolate intermediates, crystallize them, solve X-ray structures. So we've got this solved, and hopefully I'll get this paper submitted by Thanksgiving. And as mentioned, the key aspect is that you do get the intermediate, we think, but and it's cyclized. But anyway, so there you go. Stay tuned. I hope you'll enjoy reading it when it comes out. So now I'll segue to a slide. This is a slide I've created quite a few years ago, and I keep on tweaking it and updating it a little bit. But this essentially is the middle portion of my scientific career, starting is pretty much when I came to Minnesota, and ending when the NIH concluded that there were no problems left to solve in the peptide field, that everything works, and clearly, right? And so we don't need the development of new methodology. We don't need to train students to do this or anything. We don't need curiosity-based research. We don't need fundamental mechanistic studies. We just need to make drugs, and God knows what else they need. But anyhow, but it's been a fun ride while it lasted, and I hope that many of you in this room use some of this chemistry that was developed primarily in the Minnesota labs, and but of course many other contributions. I should also point out the amazing collaboration pipeline I have with the Barcelona group of Fernando Albricio, who is my postdoc. And this is one of the other nice things about a career. You live long enough, your students start getting major awards. So Fernando, as you know, got the Dovigneau Award at the most recent American Peptide Symposium. So we developed 2 resin supports. I just had a meeting with our technology transfer people at the University of Minnesota. PEG-PS has made the university close to $1 million. That's just in royalties. I believe this is the resin of the support of choice for solid phase synthesis. Then Maria Kempe, who is now a faculty member back in Lund, developed a variation of that called CLEAR, cross-linked ethoxia acrylate resin. You'll never believe who came up with that acronym. It's none other than Lin Chen with his superior knowledge of the English language. And we've also developed a whole variety of handles, or other people tend to call them linkers. PAC is one for making peptide acids, a normal end group for peptides, but as people quickly realized, if a peptide is going to be a piece of a protein and it's something in the middle, you can't have a charge at the end. You need to have a neutral end group. And at the time we started, there was no way of making peptide amides by FMOC chemistry. So Fernando and I and a few others came up with a very friendly thing called PAL. And then we went overboard with the rhyming scheme, came up with ZAL and BAL. BAL stands for backbone amide linkers, and it's truly very general. I'd say on the experimental side, the major contributors to BAL were Michael Songster, who's at Biosearch Technologies, Jordi Alsina, who is a graduate student with Fernando and then postdoc with me, and Knut Jensen, who was from Denmark and who likes to think that the BAL with a D added refers to his upper hair, or lack thereof. And who, Knut, by the way, won the Zervas Award just a few weeks ago. Again, a major focus of our research has been development of orthogonal protection schemes, and most of them are 2-dimensional. So we have a few that are 3-dimensional. Fernando's even gotten one that's 4-dimensional by using enzymes, but our preferred would be either acid being 1 dimension, either thiolysis or base being a 2nd dimension. 3rd dimension would be light, and like I mentioned, enzyme could even be used. And of course, the more dimensional orthogonality you have, the more flexibility you have in terms of what you're trying to make. We certainly have done a share of work on development of coupling reagents and conditions. A key point has been the development of mild cleavage conditions. And a particular interest of mine, again, really dating back to the influence of my father, was the management of cysteine residues. Cysteine is the only residue that something interesting can happen, afterwards. So how do you form disulfides in a controlled manner? And then I'd like to tell you about a supported oxidizing reagent I think has tremendous practical applicability. So here are some of the supports, and as mentioned, PEG-PS and CLEAR were developed in our lab. PEGA was developed by Meldal, and Tentagel by Wolfgang Rapp. From a chemistry point of view, PEG-PS and Tentagel are almost identical, but the strategy for generating them is different. We start with preformed PEG, which we derivatize, and then consider just as a very big amino acid, which we then couple onto the polystyrene, whereas Rapp polymerizes ethylene oxide onto polystyrene. But the reason these supports were so important is because they sort of reflect the amphipathic character of the peptides you're trying to build up on the support, and they're also compatible with some biological assays that have to be done in aqueous media. and clear, in spite of its high crossing, it also has many of these same properties. So in terms of our work on the construction of bridges, and here I'm talking mainly about disulfide bridges, but also extends to lactams. I'm sure it also extends to these, doing the what's Tommy Sawyer's company? Stapling, yeah. Victor and I were talking about this. We called it something else when we were doing this, right, many, many years ago, right? Yeah, carbon analogs, there you go. And so in the case of solution, the problem is when you're trying to make bridges, how do you get it to stay intermolecular within the same molecule? And the way you do that with high dilution, well, sometimes you dilute yourself out of being useful. You have to have reaction vessels the size of this room in order to get a small amount of peptides. Solubility issues are enormously important. Another issue is reduced selectivity, and if you're dealing with disulfides, how to avoid scrambling. So even if you form the disulfide, if you use a reagent that's too harsh, all this good work gets undone because it scrambles to whatever it likes to do. So our idea, and this was influenced by a paper, very influential to me, paper by Steve Mazur, was the so-called pseudo-dilution phenomenon. It's not true dilution, but the idea of having the reactive species on the support effectively achieves the same result as dilution. It makes it less likely for two species to react, and it's more likely for the intermolecular process you want to have happen. Well, that works only up to a certain point. It's clearly a kinetic phenomenon, and it's something we understand very well and have a lot of examples. Of course, by doing it on solid phase, you can also play around with what polymer you use, the solvent, and of course, you have the option of carrying out orthogonal steps. So, okay. So remember that the DTS protecting group is removed by thiolysis. But we thought, and that meant that Lin Chen, who's here, was able to actually get it to work in the lab, that you could turn this chemistry inside out and use it to, in a two-step mechanism, form disulfides. And it's great on paper, great on a slide, and it actually works quite well, but not perfectly. Some of the advantages are it's very mild and specific, simple, clean, effective, and the mechanism is irreversible because unlike regular thiol disulfide exchange, which goes both ways, in this case you have COS and it drives the reaction completion. But it turned out that one really had to be careful about the ratio of the DTS oxidizing agent to substrate. One can't just use excess DTS to drive reactions. And then when we did this reaction on resin, the DTS on resin, we got a trisulfide byproduct, which we didn't know what to do with and we were concerned about, while conversely, when the substrate was on resin, in spite of the fact that you would think we'd have pseudo-dilution, we still did observe dimeric byproducts. So I'll tell you probably a better way to do disulfides in a moment, but while we're still thinking about trisulfides, which is something that was kind of a wild thing that Arno Spatola and I would shoot the breeze about, but it turns out they actually occur in nature, and either intentionally, nature needs it, or sort of as a pain in the problem with the synthesis of products that have to meet high standards from the FDA. And so again, Lin Chen did this beautiful study trying to suggest essentially all possibilities, on resin, off resin, different protectant groups, and a very definitive study. And then with Jarina Selenova, we even found some interesting biological studies. That was all summarized in 1997. This is probably our best sort of activation protectant group for DTS. It's based on N-methylaniline, and the sulfur specifically attacks the central sulfur and forms the trisulfide. Well, recently we had occasion, in collaboration with Bob Hammer, who by now had left his high-paying job at LSU to drudge and toil in industry at New England Peptide, and we've revisited this chemistry on and on a tremendously larger scale, streamlined a lot of its features and are able to make trisulfides, which again turn out to be quite useful, and we hope to write this up quite soon. This is a really nifty idea, and it kind of turns a pseudo-dilution phenomenon on its end. The idea was, and again, this is something that Lin worked on along with Ioana Annis, who's now at Dow, and when it was later picked up by the people at Peptides International, Arno got all excited. Chris Darlock, when he was still there before he moved to Aileron, Deanna Long, who's also no longer at Peptides International. But anyhow, the idea is to take the elements reagent. It's really important to be attached at two sites. If it's only dangling on one end, this chemistry doesn't work. And so this is essentially a one-shot way of making disulfides, and it works great. Here's the mechanism. So here's the peptide with two thiols, which is made by standard synthesis, and you're trying to make it. It's captured by the Elman's reagent resin, and we put this chemistry on a number of supports, and Chris Darlock concluded the best one was clear, and even came up with a snazzy name, Clearox. Once it's captured in the second step, it's favored by the pseudo-dilution, and then once you have the product, you just filter it, and you're done. There's your pure product. Works really great. Here's an example of a peptide that they pulled out of their collection, which was hard to make by standard techniques and worked like a charm with Clearox. Since then, Les Miranda published a paper with a peptide that has about 25 amino acids, 4 disulfides. Again, just throw in the peptide with all its thiols, with its resin, set up at pH 5 or so, come back a little bit later, filter, and you got your product ready to go. So it's a procedure that is mechanically very simple. It's scalable. The chemical rationale is that at a key rate-limiting step, the pseudo-dilution applies. And I like to give it the analogy of the way proteins fold when they have disulfides, that they have these things called chaperones that kind of sequester it and prevent the undesired intermolecular side reactions occur. And another neat thing about the chemistry is it can take place at a range of pHs, but particularly pHs lower than 7. Most disulfide formation reactions take place at pH above 7, which also promotes scrambling. And so one can access challenging targets. And of course, if one is concerned about economic issues, one can recycle the support. I'm looking at Wally, and I see that I have way more slides prepared than I have time to give, but I think I've pretty much met my mission. I want to fast forward. Please close your eyes so you don't see how many we're skipping. Fortunately, I have been invited to the former Roche, the company formerly known as Roche. This is what we do in Minneapolis, like the artist formerly known as Prince, and I guess I could show the rest of these slides to those who are there. But since so many of you are from industry, I'd like to just meditate for just a moment on and sorry, Victor, I think I claim the copyright on this line. A professor professes. And first and foremost, we are educators. And we carry out research. Okay? What is the definition of research? Well, search means you're looking for something. You usually don't find it, and that's where the re comes in. Whoops. And so, of course, we want to, for better or worse, increase scholarly knowledge, but the flip side of that is publish or perish. We need to get money to support our work, so I'll be in the lobby with my tin cup during the intermission. Unfortunately, it's a part I hate. We have to administrate. We have to be role models and mentors, and I take mentoring very seriously. I like to think I mentor for life. I just last year published a paper with Elaine Schroll, who was my first PhD graduate student in 1980. I'm collaborating with Bob Hammer. I still have a paper or two to write with Lin Chen. We wind up practicing psychology without a license, and we are matchmakers, and I'll say a little bit of that in a moment. What are the professor's greatest legacy? The students. I don't have a list of them the way Victor did, but I'll never forget who told me this. It was Lyman Craig, the inventor of the countercurrent distribution, the inventor, believe it or not, of the rotary evaporator. Believe it or not, in 1940, they didn't have rotary evaporators. This is a paper that has, an experimental paper that has no references. That's really extraordinary. And he said to me, we are all students, just some of us have more experience than others. A few pictures, and then I'll close. Bruce Merrifield was a very modest man. He wouldn't be right front and center. There he is. This is the Boris Giesen, who died tragically, him with the cesium method of loading Merrifield resins. There's Bruce Erickson, also died tragically. This is the widow Woolley, the widow of D.W. Woolley, who was blind. This is Merrifield's boss. Woolley was the one who told to Merrifield, when Merrifield came up the elevator one day, said, I've got this idea. And he had it all written down in a notebook, 3 pages, in 1959. Said, I'd like to work on it. So Woolley says, give it a couple of weeks. Well, 3 or 4 years later, Merrifield had his first paper, the one that's the 5th most cited in the history of JACS. But the point is, if he'd been at a regular place, he would have been fired. He wouldn't have got tenure, right, because publisher perished, right? So Rockefeller gave Merrifield the freedom to do this. And after Woolley died, premature he had diabetes and he was blind. Another Woolley story. One time, Woolley was working in the lab late at night, and of course, since he was blind, he didn't need to have the lights on. So he was pouring from one flask to another, and he was using percussion to tell the level of liquid. So the security guard making his rounds comes in, turns on the lights, and sees this man working in the lab and just thought he had seen a ghost. Anyhow, so that's my memories, and couldn't have had a more wonderful mentor than Bruce Merrifield. I hope I've made him proud. That's me. And I've, of course, developed my own group. This is a younger Bob Hammer. There's my son, Michael. Simon Shannon, who shows that we got diversity in Minnesota. My longtime collaborator, Claire Woodward. This picture was taken on 9/10/2011. We were supposed to write a paper with Natalia the next morning, but somehow we never got to work. And at the Peptide Symposium in Minnesota, my extended family, which included, it's hard to see, but Bruce and Libby are in there. This is Petronic in the front. Again, shows you what a small world it is. You know about photolabile protecting groups? The very first one was published when Petronic was a visiting faculty member with R.B. Woodward in 1958. How do I know this? Because we had just left Hungary as refugees and were subletting Petronic's house. Okay? And did I tell you something about matchmakers? Okay, that's me and my wife Barbara, my parents at our wedding. These are Joey and Arena, who met, God knows what they were doing instead of chemistry in my lab. And there's Mark and Liz. Mark is now a very senior scientist at NIH, as is Liz. So I would go to meetings and attend weddings sort of in my spare time. And finally, the next generation, there's my son, Michael, now at Princeton, and my daughter, Deborah, who's going into family business as a neuroscientist at University of California, Santa Barbara. Thank you very much.
Thank you, George, for this historic perspective of solid phase peptide synthesis. Remind me, and why you don't tell at the NIH? Yeah, the amide bond is been 100 to 10 years old now. We still cannot perfect it. What's wrong with you?
Through many, many cycles, boom and bust of peptides, when recombinant DNA came up, peptides were dead. Combinatorial chemistry, peptides were dead. Victor, you've probably been on 1 or 2 more than I have, right? It always comes back, and so you should, it's really been great to be at this meeting and hear all the great things you're doing with this class of molecules. Victor.
And make a comment of the view of what Wally said. Okay, so That's it in organic chemistry that I know about. So if you want to do true combinatorial chemistry that's mathematically, statistically valid, you have to go and talk to George.
Okay. Let's thank George again for this great lecture. Our next speaker will